Hello everyone. Today we will be talking about few more aspects of continuity. First, let me continue what we were doing earlier. So we have solved a few examples where by using epsilon delta definition. So given epsilon, we tried to find delta with which we could establish continuity. Okay. So let us have one more example in that context, and then we will try a few different approaches. So we'll take a simple function which we know is continuous, but it is slightly different than the things that we have been doing so far. So I will define f from R to R as fx is equal to x square if x is greater than 0. Sorry, we'll define this as if x is less than 0 and x if x is greater than or equal to 0. We have drawn this function earlier and it is very obvious that it is continuous. Okay, but we will now try to use epsilon delta definition to establish continuity. Okay, see, major issue might be at a equal to 0. Okay, because if I'm talking about some point before 0 or if I'm talking about some point after 0, I can always construct a neighborhood such that that neighborhood lies on one side of the y-axis. As a result, what will happen when I have a point below 0, the functional form in that neighborhood will always be of the type x square. So things will be easier for me. Same story when I talk about right side of the y-axis. However, when I'm talking at a equal to 0, I will always have half a neighborhood where functional form is x square and remaining half a neighborhood where functional form is x. So we have to consider the case a equal to 0 separately. Okay. So right now we will talk about a not equal to 0. Okay. So what I will do is, again I will discuss the proof informally. It is your job to convert it into a proper textbook proof. So I will give you a background on how to reach delta, and once we reach that delta, it is homework that you start with that delta and write down the proof showing that mod fx minus fa is less than epsilon with that delta. Okay. So a is not equal to 0. So as I said, we will try to make sure that we stay on one side of that axis. Okay, so if a is here, how can we guarantee that the neighborhood stays on one side? One option is, we know if a is negative, then a by 2 is also negative, and it is here, correct? So we will choose delta in such a way that the neighborhood always stays to the left of a by 2. Okay. On the other hand, if a is here, then a by 2 is positive. So we will choose delta in such a way that the neighborhood always stays to the right of a by 2. Okay. So what does it mean? It means my delta should be such that this difference should be larger than delta. Okay. I mean the a plus delta should be within this. Correct. So delta should be such that delta is less than the distance between a and a by 2, that is delta is less than mod a by 2. Okay, now let us consider first case where a is positive. Okay, so sub case actually. So let a be positive and we know that x is now greater than a by 2 because x is in the delta neighborhood. Okay, and we are choosing delta as less than this. And what I want is, I want mod fx minus mod fa to be less than epsilon. Okay, so what is mod fx minus mod fa? Because now we know that we are on the right side, the functional form is x, correct? So mod fx is basically simply x and mod fa is a. So we want x minus a to be less than epsilon. Now when will this happen? This will happen when actually x minus a is less than delta also. Okay, so we want delta such that x minus a less than delta implies x minus a less than epsilon. So we could take delta as epsilon, then it will work. Correct. But of course, we have to make sure that this condition is also satisfied. So my final choice of delta will be minimum of epsilon comma a by 2 here. Okay, because a is positive. Okay, it should be less than this. Okay, delta should be less than, so you can take half of minimum of epsilon and a by 2. Okay, this is for positive a. What happens when a is negative? Let a be negative, then I know that x is also negative. So, and actually in fact x is smaller than a by 2, correct? X is smaller than a by 2. In that case, mod fx minus mod fa will be x square minus a square, correct? So this will be mod of x plus a into x minus a. Okay, mod of x plus a into x minus a, which now I can write as less than or equal to mod x plus mod a into mod x minus a. Okay, now what can I say about mod x plus mod a? Okay, 0 is somewhere here, a is somewhere here. We already know that a by 2 is somewhere here. Okay, and we know that x cannot go beyond this. We know that delta is less. Okay, so what I know is what will be the largest value. So this distance is a by 2. So if I go a by 2 on this side, what do I get? What do I get? I will have a plus a by 2, that is 3a by 2. Okay, this will be the largest value. Okay, so mod x will, if I try to stay within a minus delta to a plus delta, where delta is less than mod a by 2, then mod x will always be less than 3 times mod a by 2. Correct? Mod x will always be less than 3 times mod a by 2. So when I add it here, so this will be less than 3 mod a by 2 plus mod a, and this stays as it is. So this is equal to 5 mod a by 2 mod x minus a. Okay, is it okay so far? So what we can do, and we want this to be less than epsilon, correct? So 5 mod a by 2 into mod x minus a has to be less than epsilon. This means, this implies mod x minus a has to be less than 2 epsilon upon 5 mod a, correct? So we are going to choose delta, which is less than minimum of 2 epsilon upon 5 mod a comma mod a by 2. Okay, we are going to choose delta which is less than minimum of these two quantities, 2 epsilon upon 5 mod a comma mod a by 2. Okay, with that delta it should work. So we have now considered the cases where a is less than 0 and a is greater than 0. Now let me consider the case a equal to 0, because that is now slightly different. Okay, so case 2, a equal to 0. We know when a is equal to 0, we always have to consider two functional forms, because on this side it will be x square and on this side it will be x. So I have to worry about both the things. Can I make my life simpler? So basically I have to make sure that mod x square minus a square is less than epsilon and mod x minus a is less than epsilon. Correct? For left hand side I have to worry about this, and for right hand side I have to worry about this. But my a is 0, so basically mod x square less than epsilon and mod x less than epsilon. Now if I try to again use the same trick that we have been using earlier, if I restrict my attention to the interval -1 to 1, because anyway we have to worry about interval around 0. Okay, so if I restrict my attention to the interval around 0, which is -1 to 1, then in this range I know that x square is always less than mod x. Correct? Inside this interval x square, or you can write mod x square, it doesn't matter, mod x square is always less than or equal to x in this interval, if that is, if x belongs to -1 to 1. Correct? So it is enough to make mod x less than epsilon, because if mod x is less than epsilon, x square will automatically be less than epsilon. Okay, so if we choose delta less than 1, then we will have mod x square less than or equal to mod x. So we just want fx minus fa less than epsilon, which means mod x should be less than epsilon. That is, mod x minus 0, where 0 is a, should be less than epsilon. Okay, so my delta should be less than either epsilon or 1 because of this condition, and it should be less than epsilon because of this condition. Okay, so we have considered all cases, a negative, a positive and a 0, and we have derived delta in each case. Okay, now what is your homework? Homework is to write a textbook proof for this. That is, start with each case, take the delta that we have already derived. So start by saying that, okay, let me choose delta less than this, and show that with that delta, your fx minus fa is always less than epsilon. Okay. Okay. Now we will see one more example of one more interesting function. In one of the earlier lectures, we have talked about Dirichlet function, correct? And we proved that Dirichlet function is continuous nowhere. Okay, it is not continuous at irrationals and it is not continuous at rationals also. Now we will study Thomae's function, which is a modification of Dirichlet function, but we will prove that it is continuous at all irrational points and it is not continuous at any rational point. Okay, let me define the function. The function is interesting. So Thomae's function. So we define fx as 0 if x is irrational. Okay, and we define fx as 1 by q, where x is equal to p by q in the reduced form, that is, p and q do not have any common factor. Okay, and of course p and q are natural numbers, and I forgot to mention here, domain of my function is 0 1, so I'm not considering negative numbers and I'm also not considering numbers greater than 1. Okay, domain of the function is just 0 to 1, so p and q will be in n with p less than q, correct? Because then only the number p by q will be less than 1. And as I said, we will try to show that this is continuous at all irrationals. Okay, fx is continuous at all x belonging to q complement. Of course, when I say rationals or irrationals, I mean when restricted to domain. So Q complement intersection 0, 1, and fx is discontinuous at all x in Q intersection 0, 1. Okay, so whenever I have a rational number in this interval, then fx is not continuous. Okay, so what is the idea behind it? Again, idea is based on density of rationals and irrationals. Okay, see, for all irrationals the value is 0. Okay, and we are restricting, our domain is between 0 to 1. So when my domain is between 0 to 1, I can make this 1 by q pretty close to 0. Okay, because p and q are in n. So as n increases, my 1 by q will become closer to 0 as q increases. Okay, so that way rationals do have a chance of taking functional values near 0. However, on the other hand, irrationals all have only one value, 0. So you cannot construct a sequence of irrationals which, I mean, if you construct a sequence of irrationals converging to a rational, then the function value will be 0, 0, 0, and so on. Okay, it won't go anywhere near. So through a sequence of, it is easy to show through a sequence of irrationals that a function is discontinuous for every rational, but we won't do that. Okay, we are doing all these things to practice the epsilon delta definition because it's a very important analytical method. Okay, so first we will talk about rational numbers and we will show that it is not continuous. Okay, so case 1, A belongs to Q intersection 0, 1, and our claim is F is not continuous at A. Okay, that is my claim. F is not continuous at A. Okay, so what is A? We know A is rational, so A can be written as P by Q, and of course it belongs to 0, 1. This implies P is less than Q, and we are assuming that GCD of P by Q is 1, unless we assume that this is not a function. Okay, so we'll prove by contradiction. Okay, so see, when will it be a problem? When will this be a problem? What I want is, I want fx minus fa to be less than epsilon. For irrationals, what will happen? When I consider irrationals in the neighborhood of A, fx will always be 0 and fa will always be 1 by q. Okay, so if I can make 1 by q less than epsilon, then it is okay. Okay, when I have 1 by q less than epsilon, then it is okay. But whenever I will have epsilon which is larger than 1 by q, then for that epsilon we will be in trouble. Sorry, reverse way. Whenever because ideally I want 1 by q to be less than epsilon. But if my epsilon is chosen in such a way that if epsilon is less than 1 by q, then for those epsilon, I won't be able to make this difference smaller than epsilon for any value of delta, because for any value of delta I will have irrationals in the neighborhood and those irrationals will cause problems. Are you getting the idea? Okay, so this difference of 1 by q will always stay. You cannot make difference less than 1 by q as soon as you have irrationals in picture. So if you try to make difference epsilon less than 1 by q, then you are going to end up in trouble. Okay, so take some epsilon which is less than 1 by q. So take some epsilon which is between 0 and 1 by q. And let us suppose that it is continuous. Okay, suppose, so we are trying by contradiction. So suppose f is continuous at A, then what will happen? Even for this epsilon, I should be able to find some delta. Okay, So therefore there exists delta greater than 0 such that for every x in the neighborhood of a with radius delta, that is for every x in a minus delta to a plus delta, of course intersected with 0 1 because that is my domain, we will have mod fx minus mod fa less than epsilon. Okay, now 0 is here, 1 is here, a is somewhere here, a minus delta to a plus delta could be something like this. So when I intersect it with 0 1, it will again be an open interval, perhaps something like this. Okay, so in this interval I will always have an irrational number. Okay, so by density of irrationals, there exists some number y which is in this neighborhood, that is a minus delta to a plus delta intersected with 0 1 such that y belongs to q complement. Okay, therefore f of y is equal to 0. Therefore mod of f of y minus f of a will be 0 minus 1 by q, which is equal to 1 by q, which I know from here is greater than epsilon, and this is a contradiction. Okay, so we have established that f is not continuous at a. Okay, now we have to claim that f is continuous at all irrationals. So case 2, f is continuous, sorry, let me write case 2 first. A is rational, a is irrational, so a belongs to q complement intersection 0 1, and our claim is f is continuous at a. Okay, that is our claim, f is continuous at a. Now a is in 0 1, and so again in this interval there will be rationals as well as irrationals. So if I have irrationals, then I won't have any problem. So whenever I consider x as irrational, then fx will also be 0, fa will also be 0, so I don't have to worry about it. Okay, so I have to worry about rationals in this neighborhood. Okay, so for rationals, what will I have? I will have 1 by q, and this will be 0. F of a is 0 because a is irrational. Okay, so I have to make sure, to claim this, we have to make sure that 1 by q is less than epsilon, at least in some neighborhood. And I don't have to worry about mod because we are anyway considering domain at 0 1. So 1 by q should be less than epsilon. Okay, so will it be possible to have 1 by q less than epsilon? In majority of the cases, let us check. What happens if 1 by q is greater than epsilon? 1 by q is greater than epsilon means what? It means 1 by epsilon is greater than q. Correct? That is, q is less than 1 by epsilon means q is less than actually integer part of 1 by epsilon. At most less than or equal to integer part of 1 by epsilon. So how many possible values of q are there for which q will be less than or equal to integer part of 1 by epsilon? This number is finite. I'll have finitely many points, finitely many values of q which are possible in this range because q is a natural number. Okay, and we know that p is less than q because p by q is less than 1. So possible values of p for which p is less than q is less than 1 by epsilon is also finite. So number of rational numbers Let me repeat. So the number of rational numbers which have q which satisfies this condition is finite. Okay. So majority of rational numbers in the interval 0, 1 won't have this problem. Okay, only finitely many rational numbers will have problem. So I can choose delta in such a way that these finitely many rational numbers are kept outside because my x is here. Okay, and for some finitely many rational numbers in the neighborhood of x are causing problems. But then what I do, I will choose delta as smaller than distance of all those problem creating rationals. So in this interval, I won't have any problem creating rationals. Are you getting the idea? Okay. So let us now try to write this argument in the form of a proper proof. Okay. Uh, I am not sure whether you are clear, but try to go through the arguments again. So what I want is 1 by q less than epsilon. So which rationals will create problems? Those rationals for which 1 by q is greater than epsilon, which means q is less than 1 by epsilon. But 1 by epsilon is going to be some fixed number. So, and we know q belongs to n. So there are only finitely, so for example, if I take epsilon equal to 0.01, then 1 by epsilon is 100. So there are at most 100 possible values of q. And how many total rationals which correspond to this value of 1 by q? So p has to be less than q. So p can take at most 99 values. So at most 99 into 100, that is 9900 rationals. In fact, not even all that, because we know p by q is in reduced form. So 50 by 100, 25 by 100, 10 by 100, all these are out. Okay. So at most 9900 rationals which can cause problems. So we will choose delta as minimum smallest we will take minimum distance from all these 9900 rationals. We'll take half of that as my delta and it works. Okay. So let us try to write a proof, formal proof for this idea. So let epsilon greater than 0 be given to us. If r is equal to p by q is a rational number in 0, 1 with of course GCD of PQ less than 1, then what is f of r? F of r is 1 by q. Okay, so 1 by q is less than epsilon if and only if q is greater than 1 by epsilon. Okay, so 1 by q is less than epsilon if and only if q is greater than 1 by epsilon. So then we don't have a problem. Then in such case, mod of fx minus mod of fa, which will be equal to mod of fr, I will write mod of fr minus fa, that is 1 by q minus 0 will be 1 by q, and this will be epsilon. So that is not an issue. Okay. So we have a problem when 1 by q is greater than epsilon. Okay. So let us consider set let us consider set of all such numbers. So let a be set of all rational numbers which would possibly cause problems. So set of all rational numbers in 0, 1 with 1 by q greater than or equal to epsilon. Okay, so let me write a as collection of all p by q such that 1 is less than or equal to q is less than or equal to integer part of 1 by epsilon, correct? 1 by q is greater than epsilon means q is less than 1 by epsilon, and q is natural number, so this happens. And we know that p by q have to be between 0 1. So 1 is less than or equal to p is less than or equal to q. In fact, p is strictly less than q. Okay, p is strictly less than q. This is A. Now, as discussed earlier, A is a finite set. Okay, so A is a finite set since the number of possible values for P and Q is finite. Number of possible values for P and Q are finite. Okay, so A is a finite set. As a result, I can write A as R1, R2 up to some Rn. Okay, and our A is irrational, so of course A is not equal to Rk for any of them. So A belongs to Q complement intersection 0 1, therefore A is not equal to Rk for any k in 1 to up to n. As a result, mod of A minus Rk is greater than 0 for every k in this range. Okay, now choose delta as half of minimum of mod of A minus Rk, because we want all those rationals to be outside, correct? 1 less than or equal to k less than or equal to n. So what I have is, if mod x minus A is less than delta, then that implies that for that x, if x is equal to p by q, then q is larger than or equal to 1 by epsilon, because all others we have already included in that set. Okay, as a result, what will happen when I consider mod of fx minus mod of fa? It will be 0 if x is irrational, of course, if x is irrational, and it is equal to 1 by q, which is less than epsilon, if x is rational. So for those x which are now in delta neighborhood, fx minus fa is less than epsilon, and hence we have established that f is continuous at E. Okay, so this Thomae's function is an interesting function which is continuous at all irrationals in 0 1, but discontinuous at all rationals in 0 1. Okay, so we will stop here. Okay, try to go through both these examples again. You need to really get comfortable with the epsilon delta definition, that is very essential. So try to go through these once again, and we'll meet again. Thank you.